go very nicely. I'll do that. I'm going to be using this one. So, 1 minute. Let me unplug myself from the network. Otherwise, we're going to get this inconvenience thing. Right here. Did you receive some worksheets on Maple on LTV models?
Yes.
Not yet. Not yet.
Test model, sir.
Eh?
Test model we have, sir. LTV test model.
What?
LTV test
Yes.
model we have.
But only one.
Yes.
Okay. Because if you pass me a now it's not searching. If you pass me a USB, I can, or nobody has laptop now.
Yes. Yes.
Yes. Okay. Well, but you have a GR Tensor installed.
Yes. Yes.
Yes.
Yes.
Is it working now?
Yes. Sir.
Okay. So pass me your bring here your USBs, and now the problem is it's not recognizing the search. That there had to be some errors, and in fact I checked the equations, and yeah, there was there was error of sign in two propagation equations, the shear propagation and the electric light propagation. Signs were changed. Now this thing, now I rerun this whole thing, see, and all this is corrected now. So as you remember here, well, it was a very detailed calculation of the 1+3 equations. Very detailed, and I'm rerunning it again. I want to show you where the errors were. This one, the Raychaudhuri equation, was correct. The energy conservation also. This equation was wrong. I had put here a minus sign, and it was a plus sign. Now it is now corrected. Now it has been corrected. And then once all these things are calculated again, this is the right equation. And this was also incorrect. There was a problem, a sign problem here. And now that's all correct, and then I run it, and once you run it, you have the, this is a summary. These are the 1+3 equations, okay? But now they are correct. See, how I know they are correct? Because these equations have been derived. I'm not deriving them from Einstein equations. I showed you how they are derived from Einstein equations. But it's a very complicated process. So what I do is, these equations appear in, for example, in the article by Ellis and Van Elst. You have the equations listed as well, And they also appear in books. And I have another article if people want to see these equations derived. But I'm not deriving it every time I use them, I just take them. Yeah. Now they are very, Einstein equations second order look very compact. But in first order, they are quite elaborated, as you've seen. So I just copy them. But if you are copying something in the airplane from Chicago to Delhi, and you're tired, and these airplanes are always very uncomfortable. So I made errors. I copied them with the wrong signs. Apologize for that. But now they are corrected. Something I didn't give you is the .m file, which you can generate it if you run the worksheet. Can you run the worksheet?
The alias r11.m.
No, the alias, yeah, you need it.
Yeah.
But you also need, once you run this file, see, you save these quantities here, and then you save the whole thing into a Maple file that is called ltvsystem.m. Can you generate that file?
No, sir.
Doesn't generate. What does it say?
We have not made this program, no, sir.
You have not run this program. You have not run this worksheet.
Yes, sir.
You've run it. Yes or no? You are confusing.
No, sir.
You say no, sir. Yes, sir. No, sir. Tell me. Did you run this worksheet?
No, sir. We have not.
You have not run this. So what I can do? Pass me your
Yes,
things again. Yes, bring them here. I forgot to copy the .m file. I forgot to copy.
No, this
No,
will
no,
take.
no. It's let me do it. Let me.
No,
because-
this is so many. Everybody will come.
No.
We'll copy and give.
No, but two people. I did it for two persons. So, but I did not do it complete. So I know. Later everybody will have it, but for the course. Okay. Girls, this is very important for the following reason. You cannot run this worksheet. You cannot run it now. You can run it later with calm. It's very complicated. There are lots of calculations, lots of calculations. But what you can run, all these calculations have been stored here, which is a file that I just gave you. Right? That's why it's important. That's why you need it now, not later. Now, okay? Now you have this file. This file contains all the things that we calculate. Well, we did not save everything. We're saving the names, the information, the list of variables, and then the equations, right? The results are stored there. Therefore, if you open a fresh Maple worksheet, which is what you are going to do now, and you are going to follow me in the next one, you already have these things. You don't have to recalculate them. You have them stored, right? Okay? And this is the right way to do more serious to do more serious work in Maple, right? Because you cannot have a huge dinosaur of a file that has everything.
If we want to change something in between, so we can.
Yes, you can. You rerun it. You rerun it, and it's up to you. It's up to you. If you want, you can do as follows. There you have two choices. One, so suppose this is wrong. You want to correct. You find several errors, right? So you correct these errors. Run again the mother file. This is like the mother file. You run it again, and once you are reach here, you have two options. You may give it another name. You might give it, say, LTV system number 2, or another name, and it will store it there, and you keep the other one. Or if you give it the same name, it will overwrite the old one. Okay, you have these two options. It's up to you. Okay, but one or the other options, this is you, and it's not only for GR tensor or for tensors or general relative. Anything you do in Maple, anything, if you can store the information in a binary file. The key thing is that the binary file will only store objects that have been given and have been assigned a name, right? If you do some calculation and you don't assign a name to them, then it will not store them. You do some calculations and then you assign a name to the result or to the objects that you receive, you assign names to them. And then you tell Maple which names. See, you have to tell Maple, I think that if you don't say anything, if you just say save, it will save every name that you have assigned. But then it's going to be a very fat file, right? So it's up to you. You want to save, you want to do this save statement, is save, and then here's a sequence of all the names you want to save, separated by commas, except here. Here there is no comma, right? These are all the names, all the objects whose names have been assigned, and then you write a chain, you write a string with a path where you want to store and which name you are going to put to the file. Now this path depends on your system, right? If it's Windows, if it's Unix, if it's Mac, and depends where you want to store it. You might store it in the C drive or in the D drive or what, that's up to you, right? But this is a syntaxis. And the great utility is that you simply go to the to the binary. See, this is the save statement, and we're going to access it by the read statement. See? That's extremely, extremely useful. I don't see many people excited about that. Aren't you excited?
We are, sir.
Maybe Sunday. People are tired. Too much booze yesterday. No? No? Ah, no, sorry. It's Islamia. No booze here. Sorry. Anyway.
Strictly prohibited.
Strictly, yeah.
Strictly.
Yeah, okay. No, anyway, so you are tired. Too much domino playing. Okay, so now this is very good. This is something very useful. You will see it in a minute, but it's very useful. Okay? Now, it has been saved. Now, a good recommendation is that you save a file with the names. See, this is a file that is called names LTV, and these are all the names of the things that we saved, the way they are called, so you can call them again. It's easier. And then there is a list of variables, and then there is a string with information. Because if you just did this and saved them, and only one day has passed, then you remember. But what if you save this, and then leave them and go back to them 1 year afterwards? You don't even remember where it is stored, right? So, okay, enough talking. Now let's see what we do with it. See, and this here, you can, let me edit here, remove output. And this you can, this one you can do now in a fresh. Because you already have the file, you already have the .m file, right? Yes. Yes. You have the file as .m, right?
Yes, sir.
Yes?
Yes.
Okay, ready? So type restart. Ready? You say yes when you are ready.
Actually, sir, we have Windows system and we don't know what is the path to read that file.
C colon and ABCD you give.
But sir, it's
Path appearance with C colon you can give C colon slash file.
Take the file and
Well, that's all.
but not very
Every अरे यार क्या बात कर रहे विंडो में C colon slash and directory name.
जहाँ पर है फाइल वहाँ
That's
से
all.
निकाल कर।
Well, if you cannot fix this in 1 minute, then I'll take off and you do it later.
Yeah, because this all.
Okay, so you do that later.
Yeah, better.
Because otherwise we're going to be half an hour in that. Okay? So anyway, you get the idea, and then you do it at your own rhythm. First, we read, see, now it is the read statements. Before there were the save statements, now it's the read statements. Now, read, and this is a file, this is a Unix system, the Unix hierarchy, and this is where it is stored. It is stored here, so I read diff alias, I read LTV systems, and once these are read, then you have all the information. You have the names, the information, and the list of variables, right? Now the variables appear with the dependence because I have not declared them. I have to declare them. Once the next statement would be the declaration of the dependence of these variables. Okay? Yeah?
Yes.
Where it is, I declare them, right? So notice the output. Say, any one of these diff alias statements, what the output is simply telling you all the derivatives, up to third order, all the combinations of derivatives. You can omit that by typing a colon instead of a semicolon. Okay, so here are our equations. See, this is what we calculated in the other worksheet. Here we have it, right? So next time you want to work on this, you don't have to go back and recalculate everything. It's there. You just read the binary file, right? Now, once you work with this, and you create a new binary file and a new binary file, you can create a sequence of binary files all the time, right? And for example, if you create, let's suppose we continue this work, and then we create another binary file, so you don't have to read the first one, you only have to read the last one, except that the files get bigger, right? But you only have to read the last one, okay? And this is a very good advantage. Okay, so now we have the equations. We're going to do some basic substitutions. Replace theta by 3h. So first we declare h. Okay, first we declare h. We declare h. Okay, diff alias. And then this is what we want to substitute. See? We give names to these things. It's easier to give names to these substitutions. Now, theta is going to be equals to 3h. We substitute this in the Raychaudhuri equation, and in order to isolate ht, we solve the following equation, and whatever is the result of that equation, which will be ht, we call it ht, right? And then we give a name to this equation. So this is the Raychaudhuri equation given in terms of h, right? We do the same for all the equations, right? This we call equation of rho t. We do the same for shear propagation. We solve it, and this is equation sigma. We do the same for W propagation. We solve it. We do the same for the constraints, right? So, summary, this is what we have now. So we've modified the equations so that they are now in terms of, now, as I mentioned before, this system cannot be worked out only, you cannot just do the evolution equations because you have the constraints. The constraints might not be so easy to satisfy. So what we're going to do now is to substitute the Q-scalar and the fluctuations, right? And then the system will magically simplify. It was complicated to do it because of an idiotic error I did, but now you'll see how simple it is, right? How wonderfully simple it is. Okay, so first we declare the scalars. Now, what I noticed is that if I use this thing, rho Q is horrible, it's really ugly display, right? So what we're going to do is to call rho Q and d rho, to call it m, small m. See, it's an issue of notation, but this will greatly simplify the viewing of the results, right? So let me do this, explain this thing here, okay? Notation here, notation, and then we will denote the Q scale, the density, Q scalar, rho Q by m Q, okay? And its fluctuation d rho by okay, so that, because it is easier to see one symbol, MQ. Well, MQ, really, the way I'm going to denote it is, I cannot do MQ, okay? MQ and the other by DM, okay?
Yes.
Understood? We are agree on that? Because otherwise the notation becomes very clumsy, very clunky, right? So unfortunately I cannot use in Maple subindices, names with subindices. They don't work well with names. And sooner or later there are errors. Another possibility is to use to use a name like this, for example. I could say like rho Q, and tell Maple that this is, but then this is also clunky, because first the word rho would not appear, the letter rho would not appear, would appear the string RHO, and then the quotation marks will be appearing all the time, so it's also clunky, so it's not worth it. Okay, so believe me, it's the best solution. MQ is going to be rho Q, okay? Yeah, ready? Everybody agrees?
Yeah.
So we declare MQ, HQ, DM, and notice it's capital D, okay? Because it's a fluctuation, is this fluctuation, is rho minus rho Q, okay? It's not the relative fluctuation, it's rho minus rho Q, okay? Is this fluctuation, okay? It's not the relative one, right? Okay, so have we declared them? Not yet, okay? We declare them now, okay? Now, essentially what we're going to be substituting is this. We're going to be making this substitution here, right? Because rho, oh, sorry. Nobody noticed, see, you're sleeping. MQ plus D, okay, right? Okay? equation number 1 will be to substitute these things. We're going to what we need to substitute is, in fact, let me do another definition here. This is one thing we have to substitute. We also have to substitute ec sigma, because we know that sigma, what is sigma? Is minus the h, right? And ec w, what is w? W is what we've been calling psi 2. What is this? Is minus kappa by 6 times dm, okay? Where we have to substitute all these things, right? Okay? Because look at the system we have here. The system we have has big H, has sigma, and has W, and rho. And we want to eliminate these quantities in terms of the Q scalars, right? So this is why we do these substitutions. The first equation is we substitute these things here. It's substitute ec sigma and in ec w. We're going to substitute them in the first equation, right? And this is what we get. Oh, sorry. Yeah. Okay.
Sign again.
Okay. So now you see these are 4 equations, are the 4 evolution equations, and they have now only the Q scalars and their fluctuations appear here. But the derivatives are mixed. See? The derivatives dHt appears here, and then it appears somewhere else. dH appears here, and MQ, dNt. They are all mixed, the derivatives, right? But we're going to separate them algebraically. This is the first thing I tried, but it gave me an error, and that was because I had not written the 1 plus 3 equations correctly. But now, since they are correct, we can solve this algebraically, okay? And this is what we are going to do now. We're going to ask Maple to solve these equations and to eliminate these derivatives, right? And Maple does this very fast.
MQ.
Yes, that's true. Yeah, down. Okay. So let's define this again here, and here they are. These are the equations, and they are correct. Right? They are correct. See, this is the 1 plus 3 system in terms of scalars and fluctuations. The solutions above are the evolution equations for blah blah, for these objects here. Now, we need to check that the constraints are satisfied. For this purpose, we will use the expression for the gradients. We will need this, but have to write them correct in the new notation. Okay. You see how the M is so much better than the string rho, right? Okay. So we have the evolution equations. Now let's change. Let's check that the constraints are satisfied. If the constraints are satisfied, then that's it. That this system is correct.
Can we change rho with M? in notation?
Where?
EQR, HOQR,
Where?
second one.
Here?
No, above notation, the notation of equation.
First
Red one,
time.
in red one,
I don't understand. What's the question?
you have written equation row QR.
Ah, yeah, here in the text.
Yeah.
No, it's okay. You can. No, because it is notation. Really, it is the density, but because we cannot, people could have used, for example, row 1, or row 6, or whatever.
No,
You're
you are
saying to
talking
do
about
this.
input, no?
To
You are
do
talking
this?
about input.
Red one, red
Ah,
one.
Do
red.
this. You say to do this.
No, but he is talking about the input equation 2.
Ah,
Yeah.
yes.
Can we replace row with M?
Yes. I see what you mean. Yes, okay. You are right. Yeah. I see what you mean. Yeah, it's not this, but here,
Yeah.
like this. Right? Okay.
MQ, yeah.
Okay, to be consistent here. Yeah, fine. Looks very beautiful now. Okay. Now, once we do this, we substitute all this. We substitute all this. This we call ec sigma. And this we also use ec w, right? Yeah. Use also ec w. Yes. We first substitute. Let me do it like this interactively. First, we substitute all these things in the constraint number 2. And then we substitute the formula for HQR. And then we get 0. So constraints are, first constraint satisfied. Now second constraint is also going to be satisfied. Right? Right. Second constraint is also satisfied. So that's it. So, yeah, we already have our system. It's done, right? And this system can be worked numerically with only the evolution equations, yeah, because the constraints are automatically satisfied. So it's a system of differential equations, right? So this is, now we're going to give names to it. The equation, let's call it like this. Right? These are the equations that we need to work with. And they can be simplified a little bit. Like, for example, the first one. Let's see. I'm going to simplify, to embellish them a little bit. Okay, then the number 2 is this, and equals collect right hand side of source 2, collect this with respect to dh.
What is the meaning of SOLS?
The meaning of what?
SOLS.
The algebraic solutions.
Okay.
I'll show you in a minute. I'll show you in a minute. Okay. So here they are a little bit embellished, so they look nicer this way. Okay. Well, it's this solves. See, we have these equations here. Once we substituted, the derivatives, time derivatives are mixed up. So we need to isolate them. That's why we solve the system. It's an algebraic system, right? Your variables, your unknowns are everywhere, are scattered everywhere in the equations. So you need to solve the system in order to. It's an algebraic solution.
Okay, you solve means if these are the solution you are requiring.
Yes.
The name is assigned to it. Okay.
Yes, it's a name assigned.
Assigned.
The solution is delivered. You see, the solution is delivered as a set.
Yeah.
So
yeah.
you assign it a name.
Name.
And then you extract the elements by subindices. Okay. That's it. Here. So these are our equations. Okay. Now we can supplement this system with evolution equations for the metric functions. For this purpose, we declare the metric functions A and gamma. And this we have this, right? We supplement this by, see, these equations, they are self-consistent, right? They have all the variables are there, right? All of them. However, what we will get is a quasi-local density, and we're going to get the quasi-local Hubble scalar, and there are fluctuations. From those, as I showed you in the blackboard yesterday, we can get anything. We can get any other quantity can be computed from them, right? But the metric not directly. You can compute the metric. For example, if you have to prescribe an initial density, right? This is part of the initial conditions. We will see that in a minute. Now, this you prescribe. You give this thing, right? You give this thing. It's an initial density. It's an average initial density, right? You give it. What's a logarithm of the cotangent of the whatever a Gaussian, whatever you want. You give the value, right? And you choose it. This is input that you have to provide, right? Initial conditions. Nobody will give you the initial one. Data can give you initial conditions, but that's not, you need them to solve it. That's something you have to do. Now the system will give you a numerical, the system will give you this, right? The system, yeah, integrating that, you will solve it. If you solve that numerical, you will have an expression for rho Q, right? Agree? A numerical function, a plot, a graph, a list of numbers, but you will have this function. Now, we know that this is therefore, how do you find A? See, you prescribe this and you obtain this. So now both of these are known. So, very simple. A will be simply rho by rho Q0 1/3. Right? You can find it also like this. Okay?
This is you got from your solution, no? Rho QTR.
Yes, you get it from the numerical solution.
Yeah, solution, yeah.
Yeah, solving this, of course. Once you solve this, you can find A in this way. But you can also find A if you give a differential equation for it. and you add this different. See, these two equations can be added. See, once you have a system of differential equations, ordinary differential equations, it doesn't matter if you have 4 or you have 6, as long as they are consistent, right? Doesn't matter, you can add 2 more. There might be some numerical problems what is called rigidity. Rigidity is when some variables are very slowly varying, right, and very smoothly varying, and other variables are varying very, very rapidly, right? If all variables are varying very rapidly, then that's not such a bad situation because you choose a grid that is very dense, very thick, very, very, very dense grid, and it will work for all the variables. And the same, if your functions are varying very slowly, then you can take a large grid, right? A larger grid. The problem is when they mix. And this problem in numerical work is called rigidity. When some of your variables have one behavior, the others another, because how do you choose a grid? It can be very problematic, right? And there are some methods, some numerical methods, especially designed for this type of problems. But they are not the standard ones. Maple uses the standard Runge-Kuttra. Are you familiar with that?
Yeah.
Yes, Runge-Kuttra method to handle. See, when you ask Maple, solve these differential equations, Maple will use as the standard default method the 4th order Runge-Kuttra. Okay? So 4th order Runge-Kuttra is not good for rigid problems, right? But these things, well, we're not going to model collapse of black holes or anything like that. Rather, we're going to model evolution of density profiles. We'll see it. I have some numerical things that I'm going to show you so that you see how it works. But essentially, if suppose you want to model, this is your initial average density, right? And this is cosmic density here in the background. So what you want is some sort of overdensity that will do this, right? Intuitively, right? Intuitively, what you want is something that, remember, it's spherical symmetry. So we want the highest density at the center, right? But we want this thing the density to be diluting slowly so that asymptotically, right, as R goes to infinity, we get the background density. This is the background density. Okay? So typically you are going to choose something like this, which can be like a polynomial, right?
Yeah.
It's not going to be a wildly, we don't want an initial density that is doing this, right? We don't want that. That's not realistic.
Because in polynomial, the power
It's going
of
to be a polynomial.
power of this is reducing, no?
Yeah,
Power of variable.
something that is, yeah, for example, something I use very much is some typical, the eraser seems to have disappeared.
Near the laptop. There it is. Laptop. Near the laptop.
Right? Ah, yes. So we don't want something like this. So we want something smooth and nice, right? So, thank you. This is great. Thank you. So something that we can do is like this one defined as the background density, right? Which is a plus something that will go to 0. That can be like, for example, something like you can say some constant here, A, Something like this, right? It's an example where you fix the constants accordingly. Something like this, right? There are many simple functions that
Maybe you
can do
can
that.
take smooth
Logarithmic.
polynomial also.
You can also take a polynomial, yeah.
Of course, this is also
Log-
division of two
Logarithmic
polynomials.
function also can.
What?
Logarithmic function maybe.
Logarithm?
Function maybe.
No.
Just be careful that logarithms behave badly near zero.
Zero, yeah.
Now, there are many functions that you can choose. There's an arsenal of elementary functions. A polynomial, you can, for example, construct here. What you demand is a certain here you say rho q0 at 0. It's let's say rho q central, right? And then this condition, and then this condition. The gradient at 0 is 0. And then you demand you need another two conditions of this type. And then you have a cubic polynomial. Cubic polynomial has 4 coefficients. If you have more conditions, then it can be a quartic polynomial. But this type of polynomials are not very good as for asymptotically, because you have to declare these conditions at finary points. Anyway, there are many ways in which you can prescribe a function of this type, right? There are many ways you can do it.
But we want it to be smooth, no?
Of course, it
Yeah.
has to be C infinity.
Yeah.
At least C2, at least continuous and first derivatives continuous, minimal requests, right? If it can be infinitely differentiable, better. But at least differentiable, at least a second derivative, first derivative. The function itself continues and first derivative continues at least, okay? Now, these are, if we have this system of 6 equations, then that's it. Now, notice the following. We have not said anything about the special curvature, right? But we also have the following 2 algebraic constraints. We have these 2 algebraic constraints. See, these algebraic constraints, this is the Friedman equation. Sorry. MQ, and EM. Yeah. We have these two constraints as well. This is a Friedman equation. Now, if you derive the Friedman equation with respect to R and use the gradient law, then you obtain the second constraint. Now, these are very important because these two constraints allows us to shuffle to change the Q scalars. Like now we are using density and Hubble, but we can also use density and spatial curvature, or spatial curvature and Hubble. We can reshuffle them because we can always eliminate MQ. Any one of these 3 we can eliminate with this constraint. And any one of these 3 we can also eliminate, right? Okay? But the most useful one, as I will show you now, is the one between the one involving rho Q and HQ. Now, we have done this. These equations are for the fluctuations, the D, right? The simple fluctuations. Now let's see how the equations look for the relative fluctuations, okay? Yeah, so let me write this thing here, okay? Put a text here. Heading 2, we say evolution equations. relative fluctuations. Okay. So the relative fluctuations are, what I mean, are the dimensionless. Eh? Okay. It's delta rho. Rho. This is equal to d. I'm not going to put the parentheses just to make notation quick. By rho q. Okay. Rho q. And this is equal to rho minus rho q, all this divided by rho q. Okay. Okay. It's and then the same for H and K. H and K. Same thing. Okay? So we have to define them. So how do we define them? Say, fine. First we declare them. If alias, we declare T, R, and these are going to be called this with a small d, dm, right? dh, and dk, right? We declare them, and we define them. Say the equation for dm is going to be dm, because this is what we are going to substitute. dm is going to be rho q, mq times dm. Do you see the see? dm is dm would be uppercase dm divided by mq. So I have to substitute this. And then the equation for dh is going to be the same thing, just changing the letters. It's dh equals hq times dh. And the same thing for k. dk plus kq plus dk. Okay? So we're going to substitute all these things, right? And substitute where? Well, substitute in the evolution equation, right? The evolution equations are, let me write them here. Substitute in this equation. And substitute them here. Okay? So first, say eval subs, these three things. Okay? Even if curvature does not appear, we still substitute. Okay? So we're going to substitute this in the first equation. And this one, let's call it equation 1. Because what we are going to do is to solve the system algebraically, the same way as we did before. This type of change of variables, they mix up the derivatives, and then you solve them algebraically. That's a trick. E1, see, and then we do the same thing for all these equations. Some of them will not be changed. Well, no, I think all of them will be changed. DMT. Three. And HQ. HQD. E4. And NQT. Here they are. Now we have to resolve the system. Okay? So we say, notice that E3 and E4 are identical. They didn't change because they have no fluctuations. So basically, we can leave these two. These are identical. They didn't change. So the only ones that changed are the ones that involve fluctuations. Okay? So we only need to solve. So we can comment on this. Okay? Make a comment saying the equations E3, E4 did not change, so we only need to solve algebraically E1, E2. This is to find the derivatives of dm, so dm dh. Okay? So we do that. We say source would be solve. What we want to solve is E1, E2, and for which variables we want to solve them. For DMT and DHT. And here they are. We should we can factor them a little bit, like for example, source. Now here we extract them. Source 1, and let's say first let's expand it, how it looks, to see how it looks. We expand this. Notice how you can. No, we still need to work on them. Because why do we need to work on them?
You have to correct the term with DH and no?
Because we still have HQ here.
Yeah.
We have to substitute this.
HQT, yeah.
Yeah.
E3, from E3 you can substitute.
Yeah, but exactly. So we substitute, what we do is eval subs, right? E3, exactly, E3 above, okay. And then we can collect terms, let's say, or let's say
Expand or correct?
expand here. So first expand source 1. Now expand this. And now we can see that there are some things that we can factor. We can collect terms in terms of HQ.
And NQ.
And also kappa. Kappa and HQ appear here.
NQ is also
NQ
common,
also.
no?
NQ, yes. In fact, the best strategy is to collect by MQ.
Yeah.
It will cluster these
Yeah.
ones, and then it will factor these ones,
Yeah.
right? So let's do that. So we have, say, left hand side above equals collect right hand side above, and we say collect MQ factor, and see how it will put them very nicely. Right? Okay, so this is, sorry?
You are not correcting HQ factor or HQ also?
No, because if it collects in powers, right? So this term will be the term with 0 power. We'll leave it alone. It will only collect on here, but then it will factor this and will factor this. You can also do it. There are several ways of doing it. So when you say collect, it groups terms in powers. And this would be, this is a term where MQ appears with power 1.
But their HQ is also appearing.
No, you are not understanding. I'm saying to collect in terms of MQ only.
But why
Then,
not?
then it will consider this as a term of power 0.
No, but what? Yeah, that is okay. But why we are not collecting power of HQ also? Not
Because it is better to put the option factor so that it will factor this term rather than collect on this term. It's also possible to do.
Yeah,
It's also possible. It's another alternative. So you can see the difference. You are saying, why not this?
No, why not this? Because that is also
Okay.
common, no? Okay, same.
Same. Yes. Okay? Okay, so we call this, let's call this same. This is going to be equation DHT. Okay? This is the equation DHT. Now, let's look at the other one. Let's look at the other one. Okay. Now the other one, we also need to substitute something. What we substitute? E4. Right? E4. And this is very simple. We say simply, we don't even have to collect anything, right? It's very simple. So we say now, this is going to be equation DMT. Okay. And then let's call, we have the system. The system is well, let's see the constraints, the algebraic constraints. Okay, constraints. So the equations for A and gamma are the same. No, they're not. See, remember this equation? These two, ek at, gamma. Ek at is the same, but this is the same, and this is the same. Now, the one that will change is the equation for gamma, because dH is now HQ small dh, right? So ek, I don't know, ek gamma 2t is going to be substitute ek with h in gamma t.
The variable
It's Q. Yeah. So this is a new equation. The other one is the same, right? Didn't change. We can still change that, give it a new name for convenience, I think that's not necessary. Now, this changed. And then the other one, we have Eck, Friedman, or Fried 1, I think it was called like this. This one doesn't change, right? But this one changes. This one will change, right? Okay, so say substitute. Substitute is okay if there are no derivatives involved. But if there are derivatives involved, then it's better to use eval and subs. But if there are no derivatives, then subs is sufficient. So substitute, in fact, we have to substitute the three of them, the three things here. I have to substitute the three things. We have to substitute this. And so this is the equation, right? We can say left-hand side of the above thing divided by HQ squared. This is the same as let's say expand the right-hand side above divided by HQ squared, and this is the this looks very nice. So we call this called egg Fried. Fried 2b. So now our system, say, the new system is, well, we have E3 and E4, which are the same as, in fact, they are the same as the equations we had before, that we call them, in fact, perhaps we should call them EC. I think were MQT. This didn't change. HQT didn't change. But then we have EC, DMT, and then EC, DHT. These are the evolution equations. The constraints are, and also, in fact, we can even write them together. AT, the same. Gamma was gamma, right? Gamma 2t. Gamma t. Okay. And then we also have Fried 1, which didn't change, and Fried 2b. So this is our system. This is a new system. Okay. New system. And it's identical to the other. Right. And here's everything in terms of it's everything expressed in terms of the relative fluctuations, right? And so there is a mixed system that we can obtain in which we use the relative fluctuation of the density and the normal fluctuation for the Hubble scalar and the curvature. This is one. But it's very easy to obtain it. We just have to do the right substitutions. That's all. Okay. Now, sometimes I've been very careful to, whatever new equation I find, I give it a name, right? Now, sometimes in a very long calculation, you lose track of the names you have been
Yeah.
assigned. Now, Maple has one way of telling you all the names that you have been using. If you go to the upper part here, say, here you can, favorites, no, not here, Maple Cloud, not here, variables, here it is. Here are all the variables you define, all of them here. Here are all your variables, E1, E1, E2, all your variables, all the names you have used are here, are listed
Which we
here.
have used already.
Yeah. Notice how many of them we have used.
Yeah,
right?
yeah.
Because notice also that it has the names that were read on the binary file. Because these names are now part of the information of this worksheet, even though they were not calculated in this worksheet. But Maple is aware of them, right? So anyway, if you get lost, you don't remember if a name was previously assigned or what it is, you can always go here, and I think you can here, if you double click, you see the expression associated to that name. Okay? Yeah?
Yes.
But anyway, I cannot guarantee that you are not going to blow it, to blow it. That you are not going to do something wrong. I cannot guarantee that, because that depends on how careful you are, and depends on the practice. And it also depends on the hour, like 2 o'clock in the morning, probability of mistake of sign minus, or factor 1, 2, it's almost 99% you will do that. So 2 o'clock in the morning, unless you are very high on caffeine or nicotine, not alcohol no. See, that's why, see, great scientists who were very, very addicted to caffeine and nicotine. Albert Einstein, and Bertrand Russell, Sigmund Freud. You cannot say these people were stupid, right? But they put a lot of caffeine and nicotine. They were heavy smokers. Now tell me one scientist who was an alcoholic. None. Perhaps artists, some artists were alcoholic. But the scientist who was a, there is one. This guy, Gamow. George Gamow was an alcoholic. That's the only one I know. The only one I know, major scientist who was alcoholic. Alcohol is bad for thinking. Alcohol may be good for relaxation, for people feeling, but not for thinking. No, alcohol bad for thinking, right? Like if the pilot of your airplane had 20 cups of coffee, it's okay. But if he had 20 drinks of whiskey, so anyway.
So it means that nicotine and caffeine is good for thinking?
It's very good for thinking. Yeah, of course it's good for. I'm not saying
no,
that.
Is it proved scientifically?
It is proved scientifically, yes.
Everybody
It
starts.
is. It is proved. It is proved. Like, well, that doesn't mean, the scientific proof doesn't mean that unless you drink coffee or smoke, you are stupid. No, that doesn't mean that. Lots of people don't drink coffee and don't smoke and are very intelligent and so on.
Yeah.
But they are stimulants. They stimulate your brain. They release tension. They activate neurons. They don't kill neurons. They activate neurons. Smoking might be bad for the lungs, but not for the brain, right? Caffeine might be bad for your heart, but not for the brain. No, the brain is okay with these things, right? Say, yeah, that's true. So the point is that if it's 2 o'clock in the morning and you're running a very long Maple session, then the probability you'll make an error, like shown by my error, is very high. So best advice, 2 o'clock in the morning, you are tired, close your session and start tomorrow. Okay, so I'm going to show you after lunch how to run numerics in Maple. I'm going to show you I'm telling you these are good for numerics. Now I'm going to show you how the numerics is done. Okay? After lunch, after tea break. Okay? It says 11:21. Okay?
So once you repeat this thing about how you go to this thing, variables, just
They are in the left-hand side, left part
of the maple,
of the
no?
Maple worksheet on top. Here it says variables.
Yeah, that is what. So you have to go to maple.
Yeah, it's in a Maple worksheet. It's in a Maple worksheet.
Yeah, no, but upstairs you have to go to maple.
You have this menu.
Menu.
Well, you can hide this menu. This menu maybe does not appear in all the normally this menu appears in the worksheet. You can hide it, but the default it appears, and then all the variables you are defining, they pile up here, and if you double click on them, it will tell you.
It's very good.
This is in case you forget after many names, you tend to forget, and you tend to repeat names, right? And then errors can happen because you gave a name to something, and then you use the same name for another object, and then you forget about that. That's very simple, very frequent errors. So to prevent that, it's the only way to prevent that is first this idea of using the binaries is very good because you don't have to do kilometric, very, very mammoth, gigantic dinosaurs of worksheets. You do a worksheet of decent size, and then you store it in a binary, and then you open the next one, right? And then keep track of the names. It's just mental organization. There's no further. Maybe write them down in a piece of paper. You write down all the names that you've been using, and make comments. See, I notice how I make comments all the time.
Yeah.
Make comments. They don't have to be beautiful. They can be just plain crude text. But make comments. Because believe me, you return to a Maple worksheet, not even a Maple worksheet, you return to your notes. After 1 year, you don't remember what you did. But then if you have a small note, then you remember. So this is very important to do that. It's discipline. Lots of people don't do it. Okay? Okay, so see you after break. And now what I'm going to show you is how we actually integrate this thing numerically. Right? And, this will require some Blackboard explanation. Yeah. See, we have this system, right? Very nice, very nice. But of course, the analytic solutions we have shown, they are solutions of this system. Right? If you substitute them, eventually you get 0 equals 0, etc. Right? There are solutions. But the purpose of this is not so much, it's especially when the analytic solution, it's helpful, for example, if you want to use the models to explore something and do a quick calculation, then you use an analytic solution and so on. For theoretical explorations, for example, I worked on a problem of gravitational entropy. It's an idea, and there is a proposal on how to define gravitational entropy, and so it's nice to test such a proposal using LTV models because LTV models are exact solutions. And they describe nonlinear. They describe the full evolution of dust. We already know that dust is like a gas of particles at very slow velocities.
Yeah, displacement.
for example, cold dark matter is supposed to be a gas of this type. So we can use a model of cold dark matter, and then if there is a theoretical proposal like gravitational entropy, we use LTV. We can use LTV models to see how this proposal is implemented on those models. And this happens for lots of things, not only gravitational entropy. Like, for example, people working on quantum gravity, and they have a proposal, a theory, and they want to see how it is implemented in an exact solution of GR. Then you can use Friedman FLRW models. But FLRW models are very poor because they do not describe inhomogeneities. You can use them in Kantowski-Sachs or Bianchi models, but then this incorporate anisotropy but not inhomogeneity. So a simplest model that will incorporate simplest non-static model that will incorporate anisotropy and inhomogeneity are LTV models. So they are very good candidates to test ideas. I have an idea, I want to test how this idea works on an exact solution. For that purpose, analytic solutions can be very helpful. But for a lot of other purposes, it's even if the analytic solution is available, numerical work is more efficient, right? Now, let's see how, I'm going to show you in the blackboard, the preliminaries, how you start a work on this on these numerical solutions. For this purpose, I will work with these equations. The equations, the simplest ones that we can use are these, right? So let's write them here. And see how can the initial conditions be given and what preliminary steps we have to do, because say for numerical solutions it's important to use dimensionless variables. See? Because suppose we have density, right? Density. In fact, let's say it's mass density, not even mass energy, mass density. So what's the density today, cosmic, in the average density in the universe? How this is measured? We take a very large chunk of observed universe, let's say 100 megaparsecs, 300 million light years, and we do a counting of sources. How many sources are there? Well, you're not going to say galaxy 1, galaxy 2, because there are millions of them. So what you do, you translate light into mass, right? See, there's a galaxy, it's emitting light. So you see how much luminosity you have, how many sources in terms of light. Of course, this gives you an estimate of visible matter. We know that visible matter is not everything there is dark matter. But then there is an estimation built from independent forms, the independent ideas, that roughly there is 20 times more, between 10 and 20 times more dark matter than visible matter. For example, you see it in galaxies. You see a galaxy and you estimate how much visible matter you have by light. But then the dynamics of the galaxy, the rotation curves, gives you another estimate of how mass total, how is the total mass distributed in the galaxy. And we do, this is done for many galaxies, and it is done for clusters of galaxies. And there is another tool, is lensing. You know, gravity bends light. So if there is a very fat guy here, so the light will feel the fat guy, will bend, right? If there is a very thin person, very thin guy, the bending will be much smaller. So how much light is bent depends on how much mass is there in between. So this estimates points to dark matter being like 90% or 95% of the mass we get is dark, right? But nevertheless, we estimate how much matter is located, and we divide by the volume. We get that average cosmic density. It's of the order of 10 to the, I think the figure is like minus 29 grams per cubic centimeter. It's a very small number, right? But on the other hand, how much was the density in early universe? Density, let's say, at the last scattering surface, and it can be like 10 to the 12 grams per centimeter cube, right? Because an early universe was very dense.
Yeah.
So, how do you work with these quantities? It's impossible to. The system would be, the numerical work with these systems would be extremely rigid, because you have to start from extremely high values to very low values. And the same thing goes for the other variables. So we cannot use this. This is not very helpful, right? We need to dimensionalize the system to make it dimensionless in order to work with decent numbers, right? Numbers that maybe they go to 1/2 or 25, that maybe change 2-3 orders of magnitude, but not 40 orders of magnitude. So we have to dimensionalize the equated. So how do you dimensionalize this? For example, you have a density. The simplest way to dimensionalize is if we multiply the density by c squared here. This is density, this is mass density, not mass energy density, right? So this thing, what units this has? Well, G has units of, these are the units of G. Okay? The units of c squared are, and the units here are grams over cubic centimeter. So this goes away, this goes away, this goes away, this goes away, this goes away. So this has units, right? This, multiplying by these constants, we transform a density into length, right? You can always use normally to change units of quantities, you multiply them times fundamental constants. Which fundamental constants? Well, it depends on the problem at hand. Like if we're working with the early universe, then it might be better to use Planck's constant.
Yeah.
Planck's constant is also very handy. If we're working with gases, then Boltzmann's constant. Depends on the problem at hand.
Yeah.
Here, we're working with cold dark matter, late universe, so using now the Planck's constant is very small. It's like 10 to the minus 27, whatever units, I don't remember it has. It's very small. So this here we transform density into square centimeter, 1 over square centimeters. But it's still dimensional. So we also know that H0 is, let's say, 70 kilometers per second per megaparsec, right? Now, kilometers per megaparsec is dimensionless, right? It's one length divided by another length. So this is really a velocity. This is really the units of this is 1 over second. Now, okay, this is not length, right? So in order to transform it into a length, you would have to multiply, to divide by c. Like if you multiply this times 1 over c, then what units it will have? it will have centimeters second. It will have units of 1/centimeter. So the quantity we need is H0C. H0C will have units of 1/centimeter. Right? Okay? Yeah? Yeah, that's right. It's divided by C. Yeah. Divided by C. Yes, multiplied times 1/C. So this thing will have units of and this we can call the Hubble length, or to distinguish it from, let's call it the Hubble length.